It's an honor to introduce someone who doesn't need an introduction. Easy task. Harry Asada, thanks for being here today. Professor in mechanical engineering at MIT and director of the Darbolov Lab. Harry works in linguistics. Harry received his bachelor's, master's, and PhD degrees from University of Tokyo.
No, Kyoto.
Kyoto?
Tokyo is
Sorry,
actually
Kyoto.
eyeball.
Kyoto. And he joined MIT in 1982, which, if my numbers are correct, that means that he's been here with us for 40 years. I hope that's correct. Yes, nice. So 40 years of great contributions and great service to the MIT community and in general to the robotics community. He's had an incredibly impactful career in robotics. And I'm going to start with the simple and quantifiable, right? I was counting, and I think that he has received throughout his career 12 Best Paper Awards, like really. Paper awards in mechanical science, in ASME, in robotics from IEEE, in controls from ACC. And it's at the intersection of those three areas, mechanisms and robotics and controls, that Harry has given us a very large number of new ideas and inventions, starting from the invention of direct drive robots. I think he has the patent for the direct drive robot in 1984 with Takeo Kanade. Foundational work in geometric understanding of the dynamic of robot manipulators, the mathematics of grasping and fixturing, tactile sensing, on and on, including like a non-stop invention of innovative robotic devices. If you go to Harry's lab, every corner is filled with some new, like, cool gadget, right? That it feels like it must have taken a very long time to come up with. Harry has also been a non-stop leader in service and teaching at MIT in the mechanical engineering department with courses like 212, Introduction to Robotics, which so well integrate teachings in dynamics and controls with robotics, and a cornerstone course that many students that start their journey in robotics at MIT like to take. So, Harry, thanks for everything that you've brought in these 40 years, and thanks for being here today to continue teaching us about robotics. Thank you.
Well, thank you, Alberto, and thank you for inviting me to this robotics seminar. You've been taking care of this for many years. Thank you for that. It's surely a great honor to give a talk here. And then just to think about my 40 years of professional life at MIT, it's very special. It's so much fun to interact with world-class faculty members and fabulous students. We share the joys and the pains together, and then we share many of the unforgettable moments. Yeah, I appreciate that. With that, having this kind of opportunities, this could not be possible. So, yeah, this MIT environment is very special. Also, I thank my family. I didn't have much chance to thank to my families, but I have a fantastic family. My wife, Kumiko, and then I have 2 daughters, and then a dog and a cat, both are females. And they support me in any way that they can. Well, I appreciate that. Now, Alberto, I guess you don't know that I've been skipping my birthdays. And then in the last 20 years or so, I've been postponing many of the birthdays. I still have lots of black hair to here, and no coloring. Okay, this is natural, original the hair. Well, I have to confess that this morning I used anti-age moisturizers that my wife gave me for my birthday present, which I accepted. But other than that, I'm just Asada, and natural, And the most refreshing things to me is to think about something exciting ideas and work with my students and many things. I think Alberto talked about my old works, but those are old Harry. And new Harry, and I guess the newest Harry is to talk about Koopman lifting realizations for global unified representations of hybrid robotic systems. Here we go. Why robotics is so difficult but fabulous? Well, depending on the individuals, it may be a little different, but I know first motion is very special, right? We deal with the truly hard programs. Regular robotics, if you just take a few more steps, someone push you, going sideways, but you recover from it. This is hard to predict, hard to analyze. And in manipulations, Alberto spent his actual research life on manipulation, contact and non-contact. It's a really hard problem. And then actual friction is really nasty. Hybrid dynamics is some of the, it's still open questions. And the complexity of robot dynamics often comes from the hybrid nature of dynamics, where the multiple sets of dynamic equations, they must be switched depending on the state of the system, right? Governing equations of leg robots, as I mentioned, open loop kinematics, closed loop kinematics, changing all drastically. You have to set up these subsystems and switch over them. You can actually simulate it as a numerical simulations, but it's hard to see. That's a hard thing to look at. So the goal today is to obtain the global unified representations of hybrid dynamical systems based on the Koopman lifting linearizations and apply it to hard robotics programs. So shown here is we usually represent things in the low dimensional space, and which turns out to be very much linear. And then actually you have to segment it, as I said, in the hybrid systems like that. But we lift the dynamics using more than enough state variables. And we can find that the systems out there would be unified and actually no segmentation, no switching, no border, and a unified global representation can be obtained. This is based on the Koopman operator theory. And some of you have seen this, kind of weird equation, Kf phi equal phi, little circle times F. And it said that a nonlinear autonomous system can be represented as a linear dynamical systems in an infinite dimensional space. And I look at this, and first students got confused. Say, if you say the linear, maybe a nonlinear system can be linearized, but it is valid only in the vicinity of this particular point, right? But this is the exact linearization. It's not the typo, but the exact linearization. It is valid in the entire global space. How can we do it possible? Well, this kind of really weird mathematical expressions. Maybe high priests understand it, but not much. Everyone does that. And this came from the 1931 Bernard Koopman's original paper, PNNS paper, 90 years ago. But I give this kind of paper to my students. it's almost the Greek or Latin. You don't understand the kind of mathematics behind it. Recently, more actually, engineering side of the papers are being published by Mizit and Rowley and other people. But giving this to my students, they came back saying, I don't get it. I don't get it. It's really, I would say, counterintuitive, right? And then if it works well, it's a drastic change. So, and the kind of hurdle to go over is hard. So, I'd like to democratize this a little bit. Yeah, everyone to understand it. Yeah, I guess I took this picture from a dental service on the website. So by the end of today's meeting, I think you will see this kind of a face, and I get it. And so that's what I want to do. So this is the structure of my talk today. I'd like to demystify the Koopman operator theory. Largely the materials are coming from 2160, that's graduate subject I'm teaching, the tutorial. And then we'd like to do a conversion from function transformation to time evolutions and hybrid switched systems and whether that can be applied to it. And then after numerical examples, I presented some of my students' work, juggling multi-cable manipulations, pipe locomotion, passive walker, and then human gait analysis, and manipulation, horizontal insertions of a ring. This is something I think, because of the time constraint, I cut off this. But I know other important issues like a causality analysis using a bond graph physical modeling theory, and then finally it's going to control that's MPC and conclude some epilogues. So let me start with the something very minimum set of math background. This is Harry's just-in-time math review. I think you know it to some extent, but I know, let's see, the V is a vector space over around C, ROC, real or complex. And in the product, we use this notation, this type of bracket in X and Y. It's basically, mapped to a complex valued function. And it never been negative. And then if you swap, you have to take the complex conjugate. So if that is actually a vector, you can find this kind of inner product representations. And then when you deal with the functions, f and g, and integrated in this way. Second point, squared integrable functions, or L2, is a measurable function for which the integral of the squared of the absolute values is finite. So this is many of the functions follow this, and it's very useful properties. Next, orthonormal functions. Suppose phi I, phi j are orthonormal. Okay, and that means actually if you take the integral like this with weight wx, you get the 0 or 1. If they are the same, it takes a 1. Hilbert space is a space where we can define the inner product with some special property, the completeness. It's a little bit difficult to understand this in fully, but I know I can say that the completeness is basically the same properties, the same condition as these items. So for instance, this second one is actually interesting. So suppose you have some function, so or vector f, and represented in the orthonormal vectors. So each component is basically projection of this pointer onto this, or inner product between the two, and then that's a component. So you extend it in this direction. So you take a summation, you get the actual original function, so right, or vector, right? Yeah. So yeah, that's actually things we can do, and so first of all, people when look at this single equation, they got the really puzzled what that means actually. So yeah, well, in a sense actually from the Hilbert space viewpoint, this is also obvious, the things. But let me just explain this, through some constructions. So yeah, let's think about two elements in the F and the G in the Hilbert space where we can actually define the inner product. And think about another function G, which is involved in the Hilbert space. It can be expanded to this orthonormal basis functions of phi k. You can think about the simple Fourier series and expansion, right? So this is A is basically Fourier quotient, and which is given by this inner product, this equations, right? And the times that basis function to take a summation, you get the Fourier expansions. So in the following, sometimes a little bit confusing to use these equations. So I just call this a Fourier series expansion, although this is the general. Okay. Then we think about yet another function, f. This is actually transformations for Rn to Rn, mapping from Rn to Rn. And this function, although in this stage I should not disclose this, but later we will introduce f as the nonlinear function of the discrete time state transitions from xt to xt plus 1 is governed by f. And the function g is, in fact, one of the output you measure from this space. But in this stage, we just deal with just as functions, no notions of time whatsoever. So forget about this, okay? Erase this guy. Well, anyway, so function f, okay? And then we write g small, circle f. This represents the, compositional, equations with the, gx. That means actually g of x and x is replaced by function f. So basically g of fx, we write it this way. And then we assume this one too is involved in the Hilbert space. That said, that Hilbert space, this function can be expanded in this way. So these and bi is yet another Fourier series, an expansion like this, right? Given by this expression. So this bi, let's examine this a little bit further. And then this g is replaced by yet another Fourier series that we have introduced with the quotient ak. This is actually basis functions, right? And putting it there. Now this actually computational operations is can be distributed. So combine this one with this, each of this, and then kick out the ak outside of this inner product. You get this expression. This bi is to be back to the original. This Fourier expansion. We know this. A quotient and plugging into this guy in here, swapping I and k to summations and factor out the ak, the remaining part here. So what comes into your mind? It is actually some inner product times this orthonormal functions. So if you think about this functions and try to expand this to a Fourier series, you get the this coefficient times this, right? So this particular part is exactly this guy. So putting this one into this, we get just a single summation, and ak putting back to the inner product expression, we get this relationship. Now, cool thing here is that putting this one in this way, and then the ak. It's to be the inner product definition, and then just move this one to the end, so that phi and then this functions are back to back. Gk is the far end and here. This is basically g of fx. X is replaced by fx, right? And this can be written in this way. Just swapping the summations and the integrations, and g c is basically factored out here, and this particular part is a type of a kernel, and it's basically product of two functions back to back, right? So if you define a kernel like this, this expression is nothing but the g of fx equal some kernel integrated with the gc. As soon as you look at this, some of you feel that, yeah, that this is really linear operations. Function the gc is transformed to g of fx. And then actually it can be written in this way. Now you feel a little bit comfortable with this, but to make it more explicit, understandable for most of the engineering students, let me just use this kernel matrix representation. So we consider some grid points or sample points, or 1, 2, 3, whatever, infinite sample points, and we instantiate this kernel function to create the big kernel matrix, right? So some of you are working in the machine learning community. This kind of stuff is a very familiar things, right? Likewise, we instantiate function g of x, putting some sample point gc1 to gc2, and make actually this is kind of a vector representation of a function. And then g of fx2 can be extended this. If you use these notations, this weird equations can be represented in vector equal matrix times the vector, although these are infinite dimensional. Okay, are you feeling a little bit more comfortable? Yeah, things we are doing. Okay, great. Now we haven't reached the point yet because we have done the transformations of functions from gx to gfx. That's fine, but our goal is to do some kind of time evolution equations, right? Up to this and xt, and then how we can actually find xt plus 1. Can we get the linear transitions even though the underlying system is highly nonlinear? To do that, we can do the following trick. So good thing with this kf is that this relationship, functions are transferred to this. This can be applied to any of the functions involved in the Hilbert space. So let's pick G1, G2, G many of them, and then individually G1 is transferred by multiplying kf to G1 of f, G2 of f. That actually this kind of stuff, right? Or collectively, these can be represented in one equation. So kf times G1 go to this, kf G2 go to this, one equation. So, or component-wise, we can get this expression. Okay, now, so let me just summarize this. So f has been just been introduced in this way as a state transition equation. Okay, and the G is output. We have many outputs. Okay, so the nonlinear behavior is viewed by many points, different perspectives. Okay, now we have this G of f of x some actually instantiated at a certain sample points here, right? But remember that if we use this guy, this particular one is next time step xt plus 1. So let's replace this one by xt plus 1. Okay, they do that for every component. Okay, now interesting things is the following. I think most of the students smile after this slide. Okay, I promise. So if you look at this equation, I just concatenated all the stuff, right? And this particular, if you look at this column-wise, this column vector multiply this kf mapped to this guy, right? This guy. But if you look at this row-wise, okay, this is actually state is taking the particular value xti, right? And then all observables, g1 to gj or infinite, show that there's actually a set of values. This guy is mapped to this one corresponding to that in the same row. So if you treat these many observables are the new state variables, new set of state variables. This state is somehow transferred to this through linear operation. Okay, so so let's actually characterize that further. Well, let me just truncate it that the infinite dimensional matrix to finite dimensions, and write it in this way, and then we take the transpose of this big matrix to get this guy, and transpose this guy in here, and then at the same time kf becomes kf transpose. Okay. Now, in this case, what you like to do is to find the kind of a transformation from column-wise ones to map to column-wise here, right? So let's actually assume that the matrix A is sitting here. That applies to multiplied to this, and this times this gives this guy, and then this times this gives to this guy. If that's the case, basically, A times this actually value x naught viewed from G1 to Gm, mapped to next time value x t plus 1, and then viewed from total m things. So that's basically state transition. Time evolution can be extracted from here. And this computation is very simple. Once this kf is established, you can just, this particular part, x transpose times kf transpose equal A matrix times this x transpose. So you can get some kind of, using the pseudo inverse, you get this guy. So once you have A, we can get the transformations of actually xt to xt plus 1 with linear, transform. You feel a little bit comfortable? Little smile? Okay, great. Okay, so, but that is very easy to follow intuitive stuff, but it's not so much rigorous. So more rigorous things that can be done. And actually, we take a G1, Gm, many of them, as real value, the scalar functions in Hilbert space, and define a new state vector in the lifted space, infinite dimensional, new state. And where the original underlying system is linear like this, okay? But this can be transferred to this form where A comes from the two matrices R and Q, and then take this operations. And R comes from the inner product of all combinations of the observable output functions. So you pick G1, G2, G something, and this is computed by just the inner product. And the dimension of this is as large as your number of observables. And Q is a little bit complicated, but then basically they are all computable as in terms of inner products. Okay. Now, the proof is a little technical, so let me skip it. So at the end, we show that the gt plus 1 equal AZT, and that this A is basically observed all the kind of nonlinear functions involved in it. So let's do some sanity check. So I said the G is given by these observables. Suppose you pick the observable to be the original, also normal basis functions. Okay, this same phi 1, phi 2. Then this becomes this. And because of orthonormality, this becomes identity matrix, right? Identity matrix. And Q matrix, on the other hand, because of this orthonormal conditions, it is reduced to this form. So it's much simpler than this form. Okay, and then with use of this, A matrix can be computed, which is nothing but the Q transpose. So with this A, we should be able to transfer, time evolution from time xt to xt plus 1 can be made in this way, right? Now let's check out this, whether this is really accomplished. So let's take the right-hand side, A matrix. So I take it this guy Q over Q transpose here times this guy. And then if you multiply this to this, you get this kind of expressions again. If you look at this is nothing but Fourier series expansions of function phi 1 of f. So that's either this guy. And what is this? This guy is the next time step value. So that's phi 1 xt plus 1. So we can actually reproduce this. It's the same one as this by this computation, right? Okay. So to summarize this, originally nonlinear autonomous systems like this, and with observable, that's nothing but just an output, exactly linearized in this form in the infinite dimensional space. So now the question is, can we apply it to hybrid systems with the discontinuity? So working here, we have to switch many dynamic equations, and actually state variables may change discontinuously. It's kind of an ugly, difficult process, as I showed originally. So, dynamic equation A is valid only in the domain dA and so forth. How can we apply this? And actually, yes, it is possible to apply this, if the following conditions are satisfied. The first actually condition, the function is absolutely integrable like this. This one is automatically satisfied as far as we use the finite support. And then actually 2 and 3 are more important conditions. The discontinuity, this gap must be finite. Okay? And then number 3, the number of discontinuous points, many discontinuous points, that must be actually finite over finite intervals. And the function is of bounded variation, the number of maximum and minimum is finite. And if you read these conditions, you recall that these are the same conditions as the existence of Fourier series expansion. Well, we use other autonomous functions like Dobechi's wavelets and so forth. These conditions are slightly different, but basically it is applicable. I tried to implement it. That one spring break, I did my own programming. I noticed, I felt that I went back to my graduate student time. But I noticed that my programming skills went down significantly. So yeah, it helped me and to complete this job. And the first one, would like to confirm that once we establish the KF, one kind of an amazing thing is that no matter what the function you pick from a Hilbert space, G1, G2, G3, this relationship is valid, and then it can create the transfer from G to a GF, right? So we use the certain class of orthonormal functions for creating the KF, but using a totally different G. Can we really reproduce that one? Yeah, we tested, and here's the GFX is the truth value, right? Evaluating this at this particular point, and then this and the next point, and compare this one to the one which is actually estimated, predicted from multiplying on KF to G, and they are almost perfectly matched. And this is the case. The G is actually a cosine pi x, cosine 2 pi, perfectly matched. Maybe you can say that since we use the Fourier transform and the Fourier series expansion, so these G's are cosines so similar to that. It's not surprising, but even though you use a totally different observable functions like a polynomial x squared, x cubed, the same KF can completely create the mapping. So that's actually a good confirmation. And then with that, we constructed the A matrix here. So this is actually originally this ugly nonlinear functions. Well, I put this kind of gap over here. This is a hybrid, and the totally different type of equations are being used here with some gap over here. Even though there's actually the nasty ones, we can actually embed all this into this matrix A, and then represent the transitions in this way. And then actually, depending on the initial condition, it goes in kind of crazy, patterns like this. Solid one is actually, ground truth, and then there's, circles is basically, predicted one based on this guy. This guy, we needed a little bit more observables, but it's going almost perfect, tracking predictions. As you reduce the number of observables, errors and here, and the 33, once it is actually deviated and the deviations becomes larger, and here, the 17 observables almost impossible to produce it. Okay, so, and up to this point, if you give me nasty hybrid nonlinear equations, I can, translate it into a matrix, which is a linear, okay? But also this method is connected to data-driven method. You can create some data through simulations or experiments. So, that's actually DMD. Now let's go back to this big matrix expression. We use the KF transpose times the base concatenations of these, stuff in here, right? And then let's actually, truncate it, and then, assuming that this can be created by A times this matrix. And then we put this one in X and then Y. Skipping the middle part, we can look at the first one, Y equal AX. And then this is nothing, just simple, nothing but a simple least square estimation. A can be given by Y times X pseudo. And that is basically a basic concept of DMD. DMD uses the singular value decomposition, a little bit better numerical method, but basically, they brutally, brute force method, basically a linear relationship is assumed in the dynamic mode decomposition or DMD, and then this part is the least square, estimation. This method can be underpinned by the Koopman operator. If those conditions are met properly, yeah, this KF does exist, and then this method is correct. So yeah, this DMD has shown a little bit different development process, mostly used in the fluid mechanics community, and then nice connections are being made by Mazik and Rowley, earlier. But they take this is the fluid field, and then we take many grid points and then measure both pressure and the velocity, and then actually put it into a long vector like this, and then take this vector at every sample cycles and then put it into that Y matrix and X matrix, and then identify A matrix. Well, this maybe can be used for human gait analysis, and I gave this talk, a similar talk at the other place, and then one audience, person mapped in a major Northwestern University, asked me to collaborate on this, so I jump on it. So human gait dynamics are very complex, right? And then sensory motor and mechanisms that underpins and underlies the postural control in individuals. Very high, highly complex problem being studied for years. The gait dynamics are hybrid, but global unified representation can be obtained. So we go to data acquisitions and human gait data using a motor motion capture systems are used, and then actually put it into a whole body measurement. And my student Emily Kaminsky, get the whole data with the 39 markers on whole body, and going through that analysis, arrive at this linear equations. Once you do linear equations, great things. You can do many things like mode analysis. You can find the pose. So this is actually discrete time systems. So pose are plotted. So using this kind of unit circles. Within this circles, it is stable, and then outside unstable. But interestingly, you have many points here on exactly on the unit circle. What does it mean? This means the kind of cyclic periodic motion, right? And this motion is represented by a bunch of sine cosine here. Sitting here is something kind of stable, so to die out, will someone to push it, you just, after a few steps, come back to this. How quickly you can come back is represented by this group. Now, yeah, we look at the other people's data here. And this is interesting. This is the older lady. If you compare these two, yeah, it's significantly different patterns, right? So through this analysis, we should be able to characterize the gait analysis in some way. So this is a passive dynamic worker. To this audience, I don't have to explain this, but just the famous McGee's passive dynamic back robot is an amazing machine that can work without actuators and controls, right? Yeah, the system is autonomous and hybrid. So yeah, my student Jerry Ng, tackled this problem. It's a hard problem, but he put the guard functions as the one of the observables, and he created the models. It's basically a linear model, but I can predict pretty nicely the ones that actually this. Yeah, here it's a good agreement. As it goes a little bit farther, the departure is happening. But that's actually a linear model. And I have to say that the switching of the dynamic equations and the jump of the independent state variables have been embedded in this actually high-dimensional linear equations where no explicit switching is present. Yet the hybrid nature of the dynamics response is reproduced in the lifted space. The absence of explicit switching facilitates unified analysis. So that's great. So going to say, spectral decompositions of this A matrix, shown here, the lambdas are eigenvalues, and then and after t time steps, so starting with the initial condition Z0, we can write here in this way. So good thing is the system behavior can be examined separately with respect to individual modes. So if lambda 1 is, the magnitude is smaller than 1, this one dies out, and someone larger than 1 is going to actually crazy, and someone 1 is to sustain, right? So we did observe some stable ones, and some unstable ones, and some marginally stable ones. And we found that the kind of significant unstable poles exist outside of this unit circle, indicating that the passive dynamic worker is essentially fundamentally unstable. But we know that the dynamic worker can work stably if they start out a particular initial condition, which will not excite these stuff. Staying with this, it is possible to work stably. This is yet another work by Jerry Yang, yo-yo, two cable manipulations. Yeah, this is a hard hybrid problem, right? When both cables are slack, this is projectile dynamics, and then one taut, the other taut, and you have 4 dynamic equation to switch again. And then this is a quick simulations after we created this A matrix. And so it is to bounce and hitting this bound, this guy becomes a taut, and then hitting this edge, on the left hand side the cables becomes actually on a taut. So after this point, I showed you some good stuff, but two significant open questions in Koopman theory and the DMD exist. One is that for exact linearization, the system must be lifted to infinite dimensions. So you have to truncate it, right? And then with the finite number of observables, accuracy depends on what sort of observables you pick. That's actually currently it's needing the trial and error process. But interesting, we can gain some important insights from physical modeling theory. Yet more significant questions number 2, currently it is original theory is applicable to only autonomous systems having no control. So you can't actually do this. So what's the point? Robotics, we need controls, right? But this is not good. So we have to expand it. Yeah, we can do that, but causality is a key question. Now again, physical modeling theory tells you something very important aspect. Well, finding the good observables and actually something it is done. But this is very important to note. So up to this point, it's all mathematics. But mathematics can't solve the whole problem. So physical world, we have to know some basic physical laws, right? And this is yet another very high-level description. Physical systems are linear in structure. This is yet another statement being made by high priest. Yeah, it said the basic elements like mass spring and the dampers are linearly connected, okay, and all dynamical systems. The nonlinearity comes from the elements properties. So some of you are ECS folks. You know the Kirchhoff's voltage law, current law, and taking summations across this closed loop. If you add all the voltage, sum to zero, current sum to zero, they are all linear representation, linear relationship. Well, this one is actually expanded by our kind of good father, Hank Painter, who did actually develop the theory of bond graph and expanding that previous modeling theory using effort and flow variables, effort representing force, voltage, and pressure, and flow, velocity, current, and flow in any energy space. So electric circuit like this, we just take a summation of Kirchhoff voltage law, sum to zero. This is again on the linear relationship. And then it's translated into one junction and the zero junction. No matter what the notation you use, it is clear that the elements are basically connected linearly. So where the nonlinearity comes from, it's basically component properties. So here it's a kind of a hard spring. Stiffness goes up in this way, and E1 is actually force acting here, effort variables, and here yet another nonlinear friction properties are shown up here. So now the point is this: well, elements are connected linearly, right? So although there's actually output from individual elements constitutive law, this output is dependent variables of this input side. But let's see, this actually input-output relationship reveals some important nonlinear properties of this. So let's pick this E1 output from nonlinear element as one of the observable. It turns out very informative. So the output variables are not dependent variables or inputs, but we take these and output nonlinear element as additional state variables for lifting this systems, because they reflect some of the key local nonlinearities very much. So in this case, these are all nonlinear elements. We take the output of these elements, and then we add these into the systems, observables. And the good thing is that if you use not only independent state variables, but if you pick these output from the nonlinear elements, we can prove that the state transition equations of this independent states can be written linearly. This is reflect the fundamental linearity involved in the element connectivity. Okay, so recommendation is that independent state variables, usually we take the energy storage element here, and then actually auxiliary variables, output from those nonlinear elements, and we can proliferate other variables on these actually x and eta. You create hundreds and thousands observables, artificial functions coming out of it. Now, that point is not that actually difficult things, but the hard question is causality. So, yeah, if output function G observable you pick is a function of both in state X and then input U, you get a trouble. Because with this actually observable, we lift the space, right? We actually expand the number of the degrees of freedom, and then we take the time derivative dg dt. This includes du dt. That's actually, no, you can't do that. Well, in the discrete time form, it is actually to take the future information. So, many techniques are being developed and so far, but all also assuming that the U is linearly involved. Or, some interesting things by linear system, but we have to solve the problem at the root. So physical modeling theory provides very useful insights. Where does an anti-causal observable coming from, and how we can fix it? And then causality analysis based on the bond graph tells us how an auxiliary exogenous input reaches the auxiliary variables, basically observables, and then causing some troubles. So from causal path analysis, we found that as far as you use the state variables, independent state variables at the energy storage element, state over here, output from that element, and using that one as the observable, no way that the input, the U, is to influence this. So as far as you take the auxiliary, observables from energy storage elements outputs, no problem. But some of the outputs from the resistance comes in here, and that causes some troubles. So look at some simple problem like this. This one can be extended to a system like this. Well, I think I'm a little bit running the time, so let me skip this guy. So we can find a way to fix it. So that's the whole problem. Okay, so let me summarize this. Insight gained from physical model theory. The number one, connectivity of nonlinear lambda parameter system is linear. Okay, if you use the output of nonlinear elements, that's very informative. And then the causal path analysis tells you how we can actually find the safe causal variables. So now we have the final just 1 minute, and we have a control, control systems z equal az plus bu. Now we have safely bringing the input to u, and then designing control systems. Model predictive control MPC has been very popular. You have to know that this equation, because lifted, it is not controllable, right? Because there's so many variables, you can't actually control it, make it controllable. But as far as you use the optimal control, controllability is not required. So that's another reason. And then for MPC it's useful. But another big reason is that this is somehow approximation. So over some time frame, it may be accurate, but beyond that, it's not accurate. So as far as within some time horizon, it is accurate. That's great, good enough. So that's another reason why people use the this stuff. And actually, constraint can be represented linearly too. So this is actually Jerry's work, and he put in the MPC into this, comparing that with the naive PD control. PD control doesn't actually know where leading this is to hit the limit and bouncing back. But MPC, for C, it is likely to bounce back. So we be prepared for it. Very nice job that can be done. So our new interpretation, the formula, and then computational algorithms for constructing a Koopman operator, and has been presented. And I hope you feel comfortable with this. And the method has been applied to various systems. Can I just spend 30 seconds more? Okay, okay. Epilogue. Here are the things. And I've been working on the wearable robots for some time. And then we put the many arms in here, here, right? And unlike the robot sitting on the floor, the robot attached to our body, all kind of reaction force are acting here. And using this for a long time, people are more dexterous and working with this robot. So creating some kind of internal model how the robot is basically integrated into the body. So what is sort of an internal model people can create, right? Now I'm working on the elderly care. So elderly persons are using the walkers, and the Neville Hogan group, exploring the canes like this, and back to this, people, we use a lot of information, not just here, the seeing, the touching, the hearing, everything that comes to this, so. Yeah, we use a lot of information coming from the real systems. And then some papers in 90s or 80s, they found that the way that the human can create the posture image is based on something, structure something similar to Kalman filter. It's interesting. So keep tracking of the kind of stuff in there. But I don't think that the Kalman filter is represented in the original independent state variables. Yeah, since Newton's, we know that tell me the independent set of state variables that locate the dynamic state uniquely. Great. But I know if you use that, well, you get the kind of complex nonlinear equations, right? Instead, the human's case, it is connected to so many sensory inputs coming from the outside. I don't think our brain's using independent state variables. Maybe this Kalman filter is all linear Kalman filter. It's great, John. We don't need to use any complex Kalman filter, although it's infinite to space. Yeah. So maybe switching those things and maybe modeling artifact in the perceptual field, it doesn't exist. So we are actually, fighting and fussing, and that's actually limited to space. Something very heartbreaking things happening in Europe, right? Divided it. But imagine that, we can use many big space and high dimensional space, lifting linearization, unification, globalization, overarching stuff, and no segmentation, no switching, no border. That's great. That's something I like to talk about. So if you want to know more than this, I'm giving the ICRA tutorials on Friday. If you want to study more for spending a month, participate in the 2160. That's what I'm teaching. So this is my group. This is actually pre-pandemic. We're really missing this. These are all graduated already, so we're missing this. But that's a wonderful, wonderful teams, and I've been enjoying working with. So this is my sponsor, and that's it. Thank you.
Who wants to take the first question?
Thank you, Harry. That was really wonderful. A sort of tour de force of many things pulled together. I worry a little about the truncation. So is the size so great that it's not practical for practical problems in terms of how big of that A matrix you need to keep to use it?
Yeah, that's actually one of the most critical issues. And we had to do things in the linear domains, right? But the previous current work is basically very much a trial and error. Think about this, see what happens. And it didn't go well because the way of using that in the wrong. The Koopman operator is not properly formed. if you just jump into DMD, dynamic mode decomposition, just to make some of the data and do something, right? It doesn't provide much insight. So that's another reason, we put together this. So, and from these actually analysis, you gained some good insight as to what is missing, which particular part is really actually, need to be, supplemented. So that process is not actually complete, but I know, yeah, we get to some kind of a basis, on addressing this.
Great.
Hi, another John.
Oh, hello. Yeah, so for estimating the Koopman operator, I think part of your algorithm involves taking the inner product over the domain. So when you're taking real data, though, or rather, a lot of methods to do that kind of thing involve the assumption that your data are independent and identically distributed. But if you're taking data from just trajectories from real trials, that's probably not going to be the case. So are there any ideas about how to deal with this?
Yeah, no, John, that's important. And then actually, it is a problem for any kind of a data-driven method, right? Depending on how you collect the data. And then if you just take the all successful cases alone, you don't get the much of the unsuccessful cases, right? And the successful cases are often very dangerous and difficult to obtain. So that's why I would say that the combinations, integration between the data-driven method and more analytic method. So analytic method, and I presented for the first half, is starting with the H dynamics, which is maybe ugly, segmented. But as far as you can tell, the reasonable equations, such as actually one-leg motion versus two-leg motion. So you have some kind of years of experience in putting together some dynamic models, right? So using this, we can create those. We still need to find a better way of integrating these two, but that's the only thing that we can do. Yeah.
Okay. Thank you.
I'll take one question.
Yes.
Right towards the end, you mentioned constraints. Can you elaborate a bit if there are ways in which the space over which we're lifting can be influenced somehow if we have intuition of which constraints the dynamic system is affected by, if there's a way to explicitly exploit that?
Mm-hmm. On the other hand, more synthetic method is that you put together some constraint equations, and you can actually define those actually variables as the or lumped synthetic variables, so that then those constraints can be represented in a linear form, and then use these as observables. Then we can resolve some of the complex one to some extent. Yeah. So this gives us a great flexibility in reducing and reformulating the problem, otherwise very difficult to solve.
Thanks. Other questions?
I expected that much tough questions coming in, and there may be a few mathematicians here, and then
I'm sure Neville can ask a different.
Neville is always tough. So also he's friendly, so he won't shoot me down. Yeah. Well, would you like to try?
Okay, I'll bring the mic.
So I think you're assuming I was paying attention.
On you.
Say a little bit. The linearity of the connection structure in a physical system is perfectly true, as long as you don't have nonlinear relations between coordinate frames. So, for example, the map from say configuration variables to workspace variables, that's locally linear, but only locally linear.
Right.
Any comment on how that affects the analysis?
Yeah, right. So in that bond graph, I eliminated all transformers and those stuffs. So that's not true in general. So that's actually we face as a major limitation to the method. On the other hand, some other stuff.
So,
Go ahead.
by the way, I mean, so it turns out that all of those transformers they fundamentally have a multiplicative structure. So they are
Right.
not merely
Yes, bilinear. Yeah, bilinear. And then some recent paper, indicated that in fact, many systems, including the robotic, dynamic systems, can be represented by linear form, where input U versus a bunch of other, set variable X are coupled. Yeah, but an input U is in a sense affine, control affine, and in that case, we can actually apply some type of Koopman linearizations into that. But that's still constraining the system to some extent. So we'd like to seek even more general ones. But I know this, causality and then applicability. It's very tough questions. Back 1931, when Koopman presented that paper, there's no such a thing at that time. So the happy ending in autonomous systems. But still 100 years later, this very tough question to solve. Yeah. Yes.
Professor, this is a non-technical question. And I know this isn't a retirement party, but I would like to know, in your 40 years here at MIT, 40 plus, have you participated in any hacks on the MIT Dome? Or were you privy to the knowledge of such hacks over the years?
No, but I've been invited by the students to their parties. Now we're missing because of the COVID,
Do you know how to get up on the dome? He does. You can tell. Follow-up question. Can I have one of your favorite memories from the past 40 plus years? Because I too have a great community here and I love it here. So I would love to hear your thoughts as well.
Good to think.
And I know it's not a retirement party.
No, 40 years. Well, I have a few moments when just sorry about just research work, and I can't go beyond that, connected to MIT. But I know the very first the doctor student, his name is Kamo Yosef Tumi. When he discovered a very important, kind of algorithms, ideas, he gave me a call almost after midnight. He couldn't wait until tomorrow morning. He just called me, and then I was kind of sleeping, and I just respond to that. But I know that turns out to be a very big one. And that kind of thing happens multiple times. And then sometimes I came up with the good ideas. I call him, I'm so sorry. I know you are enjoying the nice evening, but I know I can't wait until tomorrow morning. Here's the good stuff. Do you follow me? No response, but so this is MIT, right? We have a kind of joy that once we come up with something, we like to tell this to someone else, right? That's a very precious moment, isn't it? Yeah, that other people can't enjoy it. So, we are rich in the mental and then actually spiritual things in here. That's it.
Thank you. That was probably the toughest question. Thank you very much, Harry. If you have just a moment, we'll celebrate with you. But before that, thank you very much for the awesome talk.